So welcome back. So we've been talking about astronomy and how the stars are created, how they're born, how they die, how they produce the elements that we need. We've talked a little bit about planetary science. We've talked about how we figure out the density of the planet, whether it's going to be a terrestrial planet, whether it's going to be a gas giant, things like that. From here on out, we're going to start talking about life. What do aliens need? What kind of conditions need to be on the planet for aliens to actually be created to grow and evolve and hopefully develop technology from that? And one of the big things we want to know is, what is this life based on? Now, when we say based on, we say, what are the fundamental chemical elements that the life form needs, that all life we think needs? And it turns out that water has some unique properties that no other substance in the universe has. So, what we're going to look at today is we're going to look at a number of different possible substances that life could be based on. And frankly, all of these life could be based on. But when we look at the different characteristics, we're going to see that there is only one substance that is uniquely suited for creating and maintaining alien life. So that's what we're going to look at today. Let's get started. Okay, so we're going to be talking about water, and we want to look at what are the requirements for life. So before we, figure out why is it that water is so special, let's figure out what an alien life form is going to need. And of course, that all alien life form applies to you and me and everything else that's sitting on the planet here on Earth. So when we're going to be three aspects. We're talking about the building blocks. Now, on Earth, all life is made of oxygen, carbon, hydrogen, and nitrogen. And there's a few other minor things, and potassium, things like that. But for the most part, these four elements make up pretty much all of the organic molecules that you're going to find out there. And most of it is actually carbon and oxygen, and then hydrogen as well. Most of your atmosphere is nitrogen, where what you're breathing right now is about 78% nitrogen. So people talk about, oh, I need an oxygen atmosphere. Actually, oxygen is a deadly poison. You really need something else in the atmosphere. Oxygen's only about 20%. So so when we look at the building blocks, then we want them to be common. We want things that are easily available. Now, if life depended upon uranium to function, and okay, I don't know how that would work, but it might. If life depended on something really rare like uranium or gold or something like that, then the odds of it just spontaneously being in the right combination on any given planet are pretty small. So certainly nothing on Earth is based that way. So that makes us think that life is going to just naturally evolve from common elements. And if you think about it, that makes sense, right? If if the common elements, the things that are most abundant, can support life, then we figure that most life forms are going to be based on those because it's what's available, it's what's around. Organic molecules, though, do need to be protected. Organic molecule bonds are very fragile. They can be broken apart, particularly by sunlight. And not only that, you've got all these individual molecules around. If you want to form a life form, you've got to bring them together somehow so that they can start interacting in all these complex processes that make up biology. So this tells us that we're probably not going to find life on a world that doesn't have some sort of liquid medium or an atmosphere. So it could either have a gaseous atmosphere or some sort of liquid medium. Now you're going to see that there are very few liquids that can stay liquid even when there's no atmosphere, when they're out in space. So having an atmosphere is going to be really important. But even if it's got an atmosphere, if it doesn't have a liquid medium, then probably it's not going to be able to have life because it needs to be protected from that sunlight. The second thing we need to think about is energy. All life forms need energy. That's almost the definition of life. And we'll look at that in detail later on. But if I'm going to have something that's going to grow, develop, it's going to reproduce, it's going to maintain itself from that, you don't get something for nothing. You need some sort of energy source for that. Well, the obvious one is sunlight. Plants are running based on sunlight, more or less. The problem with that is that the further away you get from the sun, the light that you get drops really fast. Remember, it's 1 over r squared. So if I'm 1 AU away, let's say I've got the full amount. If I'm 2 AU, I'm only down to 1/4 as much. So it doesn't take long before you've dropped out of range of any kind of sunlight, giving you any kind of energy that you can use. Possibly a better way is to use chemical energy. And so again, though, this can only occur on worlds that are being continually mixed, that they're volcanically active. Because you think about it, the life form is going to take in those chemicals in the environment, it's going to mix them or whatever it does to release the energy from that. There's going to be waste products from that. That's normal. There's no such thing as a perfectly efficient system. So there's going to be waste. Those chemicals are going to get used up. We need something that's going to basically break apart those waste forms and put them back into the form that they need to be taken back up by the life form from that. So there has to be a continually mixing of these elements. And here again, that means you need either an atmosphere or some sort of liquid medium on the surface. So no matter where we go, no matter what we try to envision for life forms, for alien life forms being created, we seem to need either an atmosphere or a liquid medium. And if we have a liquid medium, we probably also have an atmosphere for that. So these two methods of generating energy, sunlight and chemical energy, are pretty much the only way that we think life can evolve. And so when we get into later on, when we're classifying aliens based on their metabolism, these two pieces are going to be really important. They're basically going to be the two different major categories of metabolic processing for the life forms. Is they can get their energy from sunlight or they can get their energy from chemical reactions. So when we talk about that liquid medium, then there's a couple of things it needs to be able to do, particularly if we've got a chemically based life form. It's got to take these probably solid molecules and bring them into the cell. Well, that means those solid molecules themselves are not going to, penetrate any kind of cell wall or anything like that. So we need some sort of solvent, some sort of dissolver. It's called a solvent that's going to take those hard, solid elements, dissolve them in the liquid medium so that it can now transfer between the cell walls. So when it comes in, that fuel comes in, a cell processes it, uses that energy, and then it also needs to dissolve and let the waste come out. So we've got to transport that fuel in and transport the waste out. About the only way we know how to do that is going to be water, because things don't dissolve in gases generally. Certainly a solid's not going to dissolve anything. So we need some sort of liquid medium that can do that. So when we think about why we think all life forms are going to be water-based, then there are 5 properties that we need to look at, that we need to use to evaluate what's going to work. And you're going to see that water is not the best at all of them, but it's probably the best in the most of them. And it's always pretty much at the top. And that's not to say that you might not find some bizarre alien life form that's based on something other than water, but you're going to find that those life forms can be very fragile. And chances are that they're not going to survive for very long, even if they are somehow able to form in their own environment. So here's the 5 properties that we need to look at. So the building blocks of that liquid medium need to be readily available. They need to be something that's common in the universe. So here again, if you've got some form of liquid uranium, okay, that doesn't actually happen, but let's say you had some sort of liquid uranium, that's going to be so rare that it's not going to be possible basically for you to have life based on that. So this one is a little unusual, and we need to think about this. It needs to be less dense in its frozen state than it is in its liquid state. So what we mean by that, remember we talked about densities, how compact it is. Something that is less dense will float on something that is more dense. And you've seen this anytime you've used a pool floaty, right? So a lot of the pool floaties basically are styrofoam. There's a lot of air in them. So the tube that forms the pool floaty is going to be much less dense than the water. So you throw it out there, it floats. On the other hand, if you take a piece of lead, take a sinker or something like that, take a piece of lead, it's more dense than the water. You throw it in the water, poof, straight down to the bottom. It's going to sink. So you may wonder, well, why would I care about that? Well, let me draw a little sketch here. Let's find my mouse. All right, so let's say that this is the lake that our alien life form, our alien fishies are living in. All right, so we've got the fishies swimming under here and they're happy, right? Well, the first time they get a cold snap and that water starts to freeze, if that water is more dense when it's frozen, when it's a solid, than it is when it's a liquid, then that water, or whatever it is, that liquid medium, is going to sink to the bottom. Well, then the remaining liquid is still exposed to the cold. And so the next layer is going to sink to the bottom. Well, the remaining liquid is still exposed to the cold, and so on, and so on, and so on, until the entire lake is frozen from top to bottom, and our fishies are no longer happy. So if the liquid is more dense frozen than it is solid, that's basically going to kill off all the life form. Eventually, at some point, you're going to have a cold snap where things are going to get wiped out. So it's going to be very, very fragile. I mean, obviously, if the planet happens to maintain the absolute perfect temperature, then forever, then sure, the life form can survive. But we see how fragile life is on Earth, and we're water based. So if the liquid medium, let me draw another picture here. If the liquid medium is less dense when it's frozen than it is when it is solid. Well, let's say the cold snap comes, this top layer freezes, but it's less dense than the water. So you get this layer of ice, of frozen liquid on top that protects the liquid underneath from freezing. So this will stay liquid, whereas this will stay solid. And this is why ice fishing works. The water doesn't freeze from the bottom up, it freezes on the top, and then that insulates the water underneath. And your fishies are happy, they just keep on swimming. So this having a liquid medium where the uh, liquid is where the medium is more dense as a frozen than it is when it's liquid is going to be fatal. It's going to sink all the way to the bottom. On the other hand, if the liquid is less dense, or if the medium is less dense when it's frozen than it is when it's liquid, it'll float just like ice does. And there aren't many things that do that. Most things, the colder they get, the more dense they get. You heat something up and it's going to expand. The next thing we want is we want it to maintain its liquid state over a large range of temperatures. I mean, if it doesn't take much temperature change for this to freeze, well, then eventually it might actually freeze all the way down. We need it to stay liquid over a wide range of temperatures. That way, as the daily temperature fluctuates, the liquid medium stays liquid from that. Fourth one, it should have a high specific heat. Now, this may be a new term to you, so let me explain what that means. Specific heat is how much energy it takes to change the temperature. And if you think about it, if you've ever been swimming during the day, so the surrounding ground has a very low specific heat, so it heats up very quickly. So the pool deck, the atmosphere around it, the day gets really, really hot. And here in Phoenix, the ground gets hot very quickly. On the other hand, the pool is filled with water, and water has a much higher specific heat. So it takes a lot of energy to change the temperature of that water. And so it takes a long time for the water to heat up, and that means it's generally cooler than the environment. When the sun goes down, if you've ever been out in the desert, what happens to the temperature when the sun goes down? It gets really cold. Even in the summertime, it gets quite cold. And so that's because the ground has that low specific heat. It gives off its energy very quickly. The pool, again, though, has a very high specific heat. So it takes a lot of energy. It takes a long time for it to give off that energy. So at night, the pool can actually be warmer than the surrounding ground. So having a high specific heat means that the temperature doesn't change very quickly, and that regulates the temperature of the alien. That keeps the organism's temperature basically the same all the time. And so we want that liquid medium, whatever their body is based on, to have a very high specific heat. That way the organism can withstand any of these temperature changes. It makes it more resilient. Again, that's not to say that it couldn't survive. It just means that it's going to be really fragile. And the first time something goes wrong, you've got a mass extinction and the whole alien race is wiped out. And then finally, it should have a high surface tension. So surface tension is how the water or the liquid medium gloms together, how it forms like raindrops. And one place you may have seen this, if you've ever put like Rain-X on your car, what that does is that increases the surface tension of the water. So when you get the water, it starts to beat up like that. And you may say, well, why do I care about that? Well, we need it to have a high surface tension for life to form in the first place. Think about it. If I've got all these individual molecules, and let's say they're in the ocean, and that ocean just makes everything just kind of run off and run away and things like that, you're never going to get those molecules together to form life. On the other hand, if the water molecule sticks to itself and it forms these little globules like that, then those molecules are going to tend to be brought together inside those drops, and now you can actually get life forms to start being created. So we've got 5 properties that we want all of our possible liquid mediums to have. We want it to be very common. We want it to be the building blocks to be readily available. It should be less dense in a frozen state than it is in a liquid state. So it means it should float. It should maintain its liquid state over a large range of temperatures. I mean, if it's only going to be a liquid for 4 or 5 degrees, well, chances are it's either going to boil away or it's going to freeze. We want to have a high specific heat so that it can maintain stability, can regulate that temperature. And then finally, we want to have a high surface tension so everything can glom together and we can get that life started in the first place. So look in your class notes down at the bottom of the page. This is the table that you're going to see down there on the bottom of the page. And then there's some questions we want you to answer. So for each one of these, I want you to pause the video and figure out what is the best liquids that could work. So we're going to look at 5 possible liquids here: water, ethane, methane, ammonia, and hydrogen sulfide. Ammonia you're probably familiar with. It's a cleaning solution. Ethane is a kind of gas that you can, like natural gas that you can use. Methane, you're probably all familiar with that. That's swamp gas. And then hydrogen sulfide is rotten egg gas from that. So all of these are possible solvents that we could use to have a life form based on. So let's see which ones are the best. So which of these liquids are made from the fewest molecules? The fewest number of molecules, because the more molecules you need to assemble, the harder it's going to be for these things to just kind of randomly come together initially. So pause the video, take a look, give me the top 2 that have the least number of molecules. Pause the video, figure that out. Okay, so which 2 are made up of the least number of molecules? It's going to be water and hydrogen sulfide. So you see water is H2O, so it's only 3 atoms with that. Hydrogen sulfide is H2S, so it's also 3. All the rest of them have more than 3. Ammonia has 4, methane has 5, ethane has 8 from that. So far, water and hydrogen sulfide are our best bets. So which are the easiest to form based on abundance? Now remember, we talked about when stars are born, all of this comes out of the stars. But when stars are born, they're just hydrogen and helium. But then as they start to evolve and die, that's when all the rest of these materials are made. So the hydrogen and helium are the 2 most common elements in the universe. Helium doesn't react with anything. It's a noble gas. So it's not going to be useful for making any kind of life form. Hydrogen, on the other hand, is good. And, that's a good thing because it's like 75% of the universe. So the next 2 that are produced in star formation are carbon and oxygen. Think about it. When that star starts to become a red giant, it's going to start to produce carbon, and the larger stars will also produce oxygen from that. So the 4 most common elements in the universe are hydrogen, helium, carbon, and oxygen. Helium doesn't work, so I'm only left with hydrogen, carbon, and oxygen. So based on that abundance, which of these are made from the most common things? Pause the video, take a look, see what you can figure out. All right, so you see that in this case, it's the first 3 that are made from common things. Water is made from hydrogen and oxygen. Ethane is carbon and hydrogen, so both very common. Methane, carbon and hydrogen, again, common. Ammonia uses nitrogen here, and nitrogen is a lot less common than the others. And hydrogen sulfide, of course, uses sulfur, which is a lot less common than all of them. So based on that, the ones that are easiest formed from abundance basis would be water, ethane, and methane. All right, flip over the next page in your class notes on the back. Which liquids have the largest temperature range in liquid form? So to figure that out, you've got your boiling temperature and your freezing temperature. So if it's greater than the freezing temperature but less than the boiling temperature, it's going to be liquid. So to find the temperature range, all you need to do is take the boiling temperature and subtract the freezing temperature, and that'll give you the range. So which of these, give me the top 2 that have the largest temperature range? Pause the video, do that now. All right, which ones did you get? Well, the top 2 should be water and ammonia. Ammonia is actually the best. Ammonia stays liquid over a very large temperature range. So about 190 degrees, almost 200 degrees, that it can remain as a liquid. Water's close, it's only 100. But you may say, oh, well, that's a half of ammonia. That's true. So ammonia would be better for that. However, when you look at the others, ethane is not terrible, but not quite as good as water. Methane, again, that one's just too narrow, and so is hydrogen sulfide. So your top two here are going to be water and ammonia. All right, so which liquids have a high specific heat? Well, here all you need to do is just look at this column. The higher the number, the higher the specific heat. What that means is that the bigger the number, the more energy it takes to change its temperature. So take a look at these. Give me the top two. Pause the video and then see if you can figure it out. All right, this one should have been pretty straightforward. If you look at it, then the top two are obviously going to be water and ammonia, right? So ammonia is just a little bit better than water. This is one of the reasons why we like that it's got this big temperature range that it can remain liquid. It's hard to break those bonds and turn it into a gas from that. So here again, water's number two, ammonia is number one. So which ones are less dense when frozen in water? And so to do that, what you need to do is you need to look at the density when it is a liquid and then the density when it is frozen. And you want the density when it's frozen to be less than the density when it's a liquid. So take a look, pause the video, see what you can figure out. Okay, so ethane and methane are never frozen, so that's simply not a problem. That would be probably okay because we're not going to have all our fishies die from that. But from the other ones that do freeze, then ammonia and hydrogen sulfide, they're in frozen form, in solid form, they're actually more dense, and so their ices will sink down to the bottom. Water ice is somewhat unique because what's happening here is that when it freezes, it actually gets less dense, and this is why ice floats in water. And you've seen this every time you've had a glass of ice water. The water's going to float, or the ice is going to float in the water. Very few liquids will do that. All right. So when we bring all of this together, then water is the only substance that's good at all five characteristics. So yeah, ethane and methane are pretty good for density purposes, but they're terrible for how easy they are to form. Water and ammonia are both good for the temperature range and for the specific heat, but ammonia is very difficult to form because nitrogen's not that common out in space. So water is the best for all of them. And again, I want to stress that's not to say that we couldn't have an ammonia-based life form, because we might. It's absolutely possible. But we think that the most common types of life that are going to be out there are the ones that are going to make the best use of all five of these, and that's going to be water from that. So we're not saying that there are no ammonia-based life forms out there, because there might be. But right now, we would be tickled pink just to find an alien at all. So we focus our efforts on finding the most common type of alien. And then later, if we get lucky and we find some of these freaks like this, awesome. That'd be great. We'd love to do that. But if right now we're happy to find anything. And so therefore we're going to look in the most common place, and that's going to be water. So what is it that makes water so special? Well, first of all, obviously it's easily made. Hydrogen and oxygen are two of the three most abundant elements. And then water has this particular shape here that's going to be real important. This angle is somewhat unique among substances, and that's actually what gives it its property. So here, it's very simple. It's only three atoms, so you don't have to get a whole bunch of things in all the right places from that. But this angle here is what gives it polarity. Oxygen has a negative charge. Hydrogen has a positive charge. Now, the whole molecule is neutral. Oxygen is actually -2. So it's not electrically charged. But because the negative is offset from the hydrogen, you get a net positive charge down here in the bottom. And so that means that it works kind of like a magnet. You've got a negative end at the front and a positive end in between those hydrogens. So that means that you can see these water molecules. This is a salt molecule, so this is sodium chloride. And so the sodium and the chlorine are just bound together because of electric charge. But those water molecules actually can kind of work almost like a forklift or something. It sticks to one of the molecules and then is able to actually pull it apart from that. And this is the reason why salt will dissolve in water so easily. Well, we want something that's going to dissolve minerals easily because that's going to make it so that it can pass into the cell wall more easily. So this polarity is also responsible for hydrogen bonding. So this is water in its gaseous state, and it's kind of behind the picture here, the camera screen here for a little bit, but you can see that. So you see that when it's free, it's like this. But when it starts to cool down, these molecules, when they're not vibrating quite so fast, they actually form an extra little bond here. So I've got a negative connected to a positive, connected to a negative, connected to a positive. And so they form these kind of chains. So you need a little extra energy to break those bonds. When it freezes, they form these nice little crystals because that angle there is 60 degrees. I can have, if I have 6 of them, I'll form 360 degrees. And so I'll get a nice, perfect circle that leads it to have this nice lattice crystalline shape. Well, now it's basically like styrofoam. The reason styrofoam floats in water is because you've got all those air pockets in it. Well, that's what happens with the ice. It effectively has just these empty little pockets in here. And so that's making it less dense. So it's that 60-degree angle there that's allowing it to form these circles that gives it that lattice structure. And so it's less dense. The other reason is if I've got liquid water here, I've got this bond holding these things together weakly, but it's a little extra. So it requires more energy to not only get things moving faster, but also to break that bond. This means that it has a higher temperature at which it's going to become a gas, a higher vaporization temperature. This also allows it to have this larger range. You've got to take more energy before you can actually get the stuff to boil away. This bonding here is also why it's got a higher surface tension. And if you think about it, that makes sense, right? I've got these molecules and they're attracted to each other. So that's going to make things stick together. And so water is going to have a very high surface tension from that. And then, as I mentioned, the higher specific heat means because it takes a lot more energy to break those bonds. And so it takes a lot more energy just to change the temperature of the water. So all of these then make it so that water is an ideal choice for life to be based on. Again, I want to stress, it's not the only thing that life could be based on, but we certainly believe it's the most common. Everything on Earth is based on water for obvious reasons. Our planet is, 7% water or so. But we think that that's going to be common elsewhere as also. So this then becomes what we define our habitable zone to be. Since we're looking for water-based life, because we think that's the most common, then the region around which the conditions are just right, and by just right, we mean when it has liquid water. So as long as you're far enough away from the sun that you can have liquid water, that is our habitable zone. So if you're in too close, if you're in so close that the water becomes a gas, it's too hot. It's not going to be habitable. On the other hand, if you're too far away from the star and the water here starts to freeze, that's too cold. That's not possible. So you've got to be in this Goldilocks zone where it's not too hot, not too cold, and it's just right. All right, so I'm going to introduce the next major form that you're going to be using here, the next chart that you're going to be using. This is going to be so important because this is where you're going to find out if you've actually found your habitable world. So water, it turns out, depends, the phase of it, solid, liquid, or gas, depends not only on the temperature, but also on the pressure. So for example, if you've ever played with dry ice is frozen carbon dioxide. You seen that? And so what happens is that you've got this solid ice that turns directly into a gas. You'll never see liquid carbon dioxide from that. It sublimates. It goes straight from a solid to a gas. That's because at atmospheric pressure, dry ice is kind of like down here. It never moves into the liquid state. It just goes straight from a solid to a gas. Now, if you're in space, water ice does exactly the same thing. If there's no pressure, this particular diagram is for water. So if I'm out in vacuum, then the atmospheric pressure here is going to be really, really low, close to zero. And so you'll have solid ice that just goes straight into a vapor and it'll start to just smoke from that. And this is, of course, what leads to comets and their tails and things like that. So if you took an ice cube and you threw it out an airlock at the space station, it's going to start to smoke. And it's going to just go straight from a solid into a gas without passing to a liquid. Other places that you may have seen this, you may have heard that when you're up high on a mountain, it takes longer for things to cook. Well, that's because the boiling point has been lowered. And so it boils at a much lower temperature from that. So we not only need to know the temperature of the planet, we also need to know the atmospheric pressure of the planet. Now, this will always be given to you. The simulator will determine that based on the model of the planet. So you're not going to have to calculate this. You are going to have to calculate the temperature, and we'll get there in just a second. But all you need to do is you find your temperature in Kelvin, not in Celsius, make sure that you're in Kelvin, and then cross-reference with your atmospheric pressure. So 1 atmosphere is Earth normal. So our atmosphere is 1 atmosphere. So if it's 10 atmospheres, that's 10 times as thick. If it's 0.1 atmospheres, it's a tenth as thick. So you see that right here, water at Earth normal atmospheric pressure turns into a liquid, goes from solid to liquid at about 273 degrees Kelvin. And then it boils right here at about 373 degrees Kelvin. So that line right there represents our normal Earth surface pressure water. If you go up higher into the atmosphere, like you go up on the top of a mountain or something like that, well, now the atmospheric pressure is lower. And so now you see that we're going to reach a boiling point at a lower temperature. It's going to be less than 373 degrees. Well, since the water's not as hot, you're going to have to cook your food longer. All right, so let's do some samples here. So the Morex is listed in the chart here. It says that your temperature is 350 degrees and your atmospheric pressure is 1 atmosphere. Pause the video. What is the phase of water, solid, liquid, or vapor, on the surface of Morex? Pause the video. Figure that out now. All right, so the temperature is 350 degrees. That's right here. The pressure is 1 atmosphere, so I go up to here, and you see that I'm in the green. I've got liquid water. So if this were your world that you were hoping was habitable, and you end up in the green, you win. You have found your habitable world. So in this case, it's going to be liquid. All right, let's take the next one. So Dragel has a temperature of 350 degrees Kelvin. The pressure is 0.003 atmospheres. Is that a thin atmosphere or is that a thick atmosphere? That's really thin. That's like Mars or less. So using that, I want you to figure out what is the phase of water going to be. Same temperature. Take a look. Same temperature as it was on Morex, but now the atmospheric pressure has changed. Pause the video. Figure out the phase of the water. Okay, you got it? So again, we're going to start on this 350 degree line right here. We're going to go up, but we're only going to go to 0.3. Now notice how this is red. It's 0.01, 0.02, 0.03, 0.04, 0.05, 0.06, 0.07, 0.08, 0.09, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so it's a logarithmic scale. So 0.003, this is 0.001, so 0.003 is going to be right about here. You need to read this very precisely because sometimes it's going to be kind of right on the border, and you can get it wrong if you're not being very careful with it. So this is 0.001, 0.002, 0.003. And when we come across to 350 degrees, where are we? Vapor. So even though the temperature is the same between these two planets, the atmospheric pressure is so low on Dragel that it's going to become a vapor rather than liquid. All right, let's do the last one. This is Telmaron. So our temperature now is 150 degrees Kelvin. Well, on Earth, it would be frozen, right? That would be absolutely frozen. So, but is that going to be the case here? We don't know. We're going to have to look at the atmospheric pressure. So we're going to take 150 degrees. That's going to be right here. You can probably already tell the answer, but let's work it out. So we're going to go up, and we're at 100 atmospheres right here. So what is the phase of water? Pause the video. You got it? Okay, yeah, it's going to be solid. So this is also not going to be a habitable planet. It's too cold. So even with the higher pressure, it's too cold. All right, now let's do some real ones. Let's look at the moon. So the average dayside temperature of the moon is 400 degrees. The atmospheric pressure is very, 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 very small. It's basically zero. It's 0.15 zeros and a 3. So we're going to stay all the way at the bottom because you're going to be able to figure that out. If we come down here, you see we've got 400 degrees or 400 degrees Kelvin. What's the phase going to be? Yeah, it's going to be vapor. So this is why ice is actually not terribly common. It's only in the shadows where the temperature is very cold. And you see the temperature's got to get down to, 150 Kelvin or so like that before you're going to have ice anywhere on the moon. How about on Earth? So pause the video. I want you to figure out what's the phase of liquid water on Earth. You got it? Were you surprised? So this TEFF means effective temperature. So this is the temperature only due to the sunlight from the sun hitting the planet. Okay, so it ignores everything else. So we've got 183 degrees Kelvin. That's how hot our planet would be, and then just from the light from the sun. And then the pressure is 1 atmosphere. Uh-oh, the phase should be solid. And yet Earth certainly has liquid water, doesn't it? So what's happening is there's something missing here. There's something that our effective temperature is not bringing into play, because this is just the temperature of the sun shining on the ground. But there's something in between us and the ground, isn't there? Yeah, there's our atmosphere. We'll get into that later, what effect the atmosphere has. But in this case, you can see that the atmosphere must be raising the temperature of the planet, because 183 degrees Kelvin, well, that's below freezing. The whole planet would be frozen based on that. All right, so that's where we're going to stop. We're going to give you some practice with the water phase diagram. I strongly recommend that you download that water phase diagram from the web, from Canvas, and then print that out and use that rather than using the tiny picture that you've got here. It's going to be a little bit easier. So go through your list that we've given you a number of different hypothetical planets. We give you the temperature, we give you the atmospheric pressure. We're just seeing if you can use the chart. Okay, so now you've seen why it's important that we have water and why we choose liquid water to be our basis for where we're going to find life, what our habitable zone is defined upon. The habitable zone is defined by where water can be in a liquid state. If it's too cold and it's frozen, we're going to assume there's no life there. If it's too hot and it's a gas, we're going to assume there's no life there as well. And again, I want to stress that's not to say that it couldn't be based on one of these other substances, but we need to find the most common ones first, and then we'll start going to look for the freaks. The other thing that we talked about was how to use that water phase diagram, and that's going to be very important. When you're doing your project, you're going to find the star, you're going to figure out the characteristics of the star, you're going to see if it has a planet. If it has a planet, you're going to see if it's a terrestrial world. If it has a terrestrial world, your goal is to figure out the temperature of the planet, the surface temperature of the planet, and then you'll use the water phase diagram to determine if it's habitable. If it comes out in that green area, you win. You just found your alien world. All right? We'll see you next time.